Hey, welcome back here. Thanks for choosing to look at this problem. What we're going to do here is look at a situation with momentum and projectiles kind of combined together. So momentum, a topic that we're studying right now. The projectiles portion, a good review of some stuff we've already covered with you guys. So here's the situation. We've got a 10-gram bullet traveling at 620 meters per second. It embeds itself in a 1.5 kilogram block of wood. Initially, that block of wood's at rest on a tabletop, and we know how high the table is there. What we're interested in is how far horizontally that block and bullet combination end up landing off the edge of the table. Okay? So, what we're going to be looking at here is a situation where we have to figure out the velocity that this block leaves the table at, okay? Maybe I'll call it, let's say, V prime, all right? I need to figure out, once the bullet hits that block, what kind of velocity is this thing going to have as it leaves the table? First of all, just by looking at the situation, we know that V prime is only going to be in the x direction, okay? That there's not going to be any vertical component to that velocity. It's only going to be horizontal, all right? Now, the way that we'll find V prime will be by using our conservation of momentum. All right. So what we know is that the momentum, if you will, of the bullet plus the momentum of the wood block before any type of collision has to equal the momentum of the bullet and wood block put together, because remember, this is going to be an inelastic collision at the end. Okay. So again, the left side of our equation is before the collision happens between the bullet and block. The right side is after the collision between the bullet and block, okay? So to find momentum, we're just going to take mass times velocity again. And so for the bullet, we know the mass is 10 grams. Now you have to be careful here with your units. That's going to be 0.01 kilograms multiplied by its velocity, which is given at 620 meters per second. Plus, okay, the momentum of the block of wood before the collision, well, that's going to be 0 because it's at rest, is going to have to equal the momentum of the combination of these. Well, okay, the mass combination of this is 1.51 kilograms. That's the combination of the block of wood, which is 1.5 kilograms, and the bullet, which was 10 grams, okay? Multiplied by what we were calling V prime, the velocity of the two stuck together. So I can easily solve this for V prime now, and I get a velocity of 4.1 meters per second. Now, that's the velocity that the block of wood has as it leaves the table. Again, it will be purely in the horizontal or the x direction. Now, the next part of the problem involves the projectile portion. Now, this is a review of some stuff we've studied earlier, but good for us to keep this in mind. This is the sort of thing that they like to do on AP exams, is combine a bunch of different types of topics here. So I need to now use my equations from projectile motion to figure out the horizontal distance that this bullet and block combination would end up landing, okay? Well, the first thing I want to use is the fact that they told me the height of the table is 0.75 meters. Okay, so that means this dy over here is 0.75. Okay, I'm going to end up using that to figure out, first of all, how long that block is in the air, because the only thing working on the block in the y direction is gravity. All right, so what I'll end up using is the fact that the distance traveled, in this case in the y direction, is going to be equal to 1/2 times gravity times my time squared. Now, I'm able to use that equation because, again, I have no initial velocity in the y direction, so I don't need to worry about that component of that equation. So just plugging in here, I know that my dy is 0.75, 1/2 times 9.8, and I can solve for my time here. Okay, when I calculate that out, I end up getting a time that this block is in the air of 0.391 seconds. Okay, now that I know my time that this block is going to be in the air is 0.391 seconds, all right, I can simply use this to figure out my d sub x. Remember, this d sub x here is what I am looking to try to find. That's the ultimate goal of the problem, what it's asked me to find. And what I'll just simply do is to say, okay, well, v prime, which is in the x direction, is equal to that distance in the x direction divided by the time that it spends in the air. Okay, so I know v prime was 4.1 meters per second. I am trying to find d sub x, and my time now we said was 0.391. So I can do a little calculation there, and I'll end up getting a distance that this thing travels equal to 1.6 meters. Thanks for joining the Sioux Falls physics teachers here. We have a ballistic pendulum problem. We're going to be firing an 8-gram bullet into a 2-kilogram block of the ballistic pendulum. The ballistic pendulum is originally at rest. The bullet does embed itself in the block, and the combination of the bullet and block swing upward to a height of 0.24 meters. What we're asked to do here is figure out how fast that bullet is going when it leaves the gun. Okay, so we have a situation here where we're going to have to use both conservation of energy and conservation of momentum. Okay, the conservation of energy portion is going to occur over here. If you think about the diagram right here in this part of the diagram, all right, this is going to be your conservation of energy. We're going to have some potential energy here as a result of this thing swinging upward 0.24 meters, and we're going to be able to figure out that potential energy and use that to figure out the kinetic energy then that the block has when it's moving. Once we do that, that will allow us to essentially find the velocity that that block starts moving at that point. From that point, then we will start looking at conservation of momentum. All right, and that is kind of the left side of the diagram, if you will. The bullet leaving the gun and then colliding with the block is going to be a situation of using conservation of momentum. All right, so let's go ahead and get started here with it. Let's go ahead and start first of all with looking at that conservation of energy portion of the problem. So what we're going to say here is that the kinetic energy of the situation here, the 1/2, is equal to 1/2 mv squared, and that's going to be my bullet and block combination here after the collision already happens. Remember, conservation of energy is this portion of the situation over here on the right-hand side of my diagram. So the kinetic energy, 1/2 mv squared, plus the potential energy that we start with, mgh, okay, this is the beginning part, right, when the bullet collides with the block, has to be equal to the kinetic energy plus the potential energy at the highest point, okay, or at the upward swing that we have, all right? So to make this a little simpler here, one of the things that we can do, if you remember back to conservation of energy, these all contain the mass, and the mass that we're canceling out here would be the mass of the bullet and block together. All right, so we don't need to include those in there. The goal with this is for us to figure out the initial velocity that the bullet block combination starts moving at. Okay, so that's going to be my unknown. So I'll have 1/2 v squared. I'm going to have no potential energy when the bullet and block initially come together. Afterward, when it swings up to its highest point here, I have no kinetic energy because it's temporarily going to be at rest there for an instant. So I have no velocity, no kinetic energy, and all I have is my g, 9.8, times the height that it goes up, 0.24. Okay? So working all of this out, I can figure out the velocity that bullet and block have together here, and that velocity ends up being 2.1 2.7 meters per second. Okay, now the reason it's important for me to know that velocity is because now we're going to transition into a conservation of momentum problem. So what we're going to look at now is we have the bullet leaving the gun, all right? So we're going to have the mass of that bullet times its velocity, okay, v1, which is what we're essentially trying to find in our problem here. That's our ultimate goal here, is the initial velocity of that bullet, all right, plus the mass of my block, okay, times its velocity, which is going to be 0 here to start out with, is going to have to be equal to, now remember, after the collision, these are going together. So we're going to have mass of bullet plus mass of block times v prime, if I can call it that. Okay? All right. Now v prime is going to be the 2.17 that we just calculated. That's the velocity of the bullet and block combination after the collision. So let's start plugging in some numbers here. Again, remember our goal is to figure out what the velocity of the bullet is as it leaves the gun. All right. The mass of the bullet was given to us as 8 grams, so that's 0.008 kilograms. Again, don't forget to convert those units, times v1 plus the mass of the block times the velocity of the block initially is going to be 0 because this velocity of the block is 0. It has no movement before the collision. That's going to equal the mass of the block and the bullet together, so that's going to be 2.008 kilograms times that velocity of 2.17. All right? So, working this out, I will be able now to solve for the velocity of that bullet, and to calculate that out, I'll end up getting a velocity for that bullet of 544 meters per second.
Well, hello everyone. Welcome back with the Sioux Falls physics teachers. Today we're looking more at conservation of momentum. This is another one of those very frequent combination type problems. We have our collision, a cement truck traveling at a certain velocity runs into a pickup truck, and then we also have a portion of this problem that's going to deal with energy. It says the two vehicles stick together and travel with a coefficient of friction of 0.65 along the road. Calculate the distance that the wreckage travels before coming to a stop. So we're going to start here, and we're going to begin then with the conservation of momentum part. So again, remember, basically conservation of momentum says we want to add the two initial momentums of the two objects. That's going to be equal to the final. Notice that in this case, right offhand, it says that the two vehicles stick together. So at that point, we can just treat that as one momentum value, the two vehicles together combined as one object. Well, the momentum of the cement truck would be given as its mass times its velocity. Now notice that it also does say then that the pickup truck is initially at rest. So that means that it will initially have 0 momentum. And then finally, to calculate the momentum of the two things together at the end, we would simply combine the two masses, that'll give us our final mass, and multiply that times our final velocity. So for the cement truck, we have 25,000 kilograms as its mass. It is moving reasonably slowly, though, with a velocity of 5 meters per second. Add 0 for the momentum of the pickup truck. And then afterwards, we do already have the two mass values, 25,000 again for the cement truck, and an additional 3,000 for the pickup truck. And that would be multiplied times the final velocity. Now notice then that when we multiply that out, solving for final velocity, we will get a final velocity of the two together of 4.46 meters per second. Now that we have the velocity of the two, now is where we need to start looking at how that coefficient of friction is going to work into this. And again, these are good problems for review, because remember that the easiest way to work the coefficient of friction into a motion problem is by considering the work that will be done by friction. So in our conservation of energy equation, we can write it this way. Initial kinetic energy plus initial potential energy. Notice that we won't have any change in potential energy for this particular problem. Plus work is equal to final kinetic energy plus final potential energy. Now notice again, of course, there's no change in potential energy going on, so we can get rid of both of those immediately. Also notice then that we now, because we have the velocity, have the information that we need to find kinetic energy. Okay, so we know that kinetic energy is going to be 1/2 mass times velocity squared. This would be the kinetic energy of the two immediately after they collide. Okay, then we're going to add to that work. And notice then that work is force times distance. In this case, it is friction that is doing the work. And that gives us our final kinetic energy. Well, if they are coming to a stop, final kinetic energy would be 0. Okay, now we can start plugging in our numbers immediately after the collision. We saw earlier the mass of the two. That would be 28,000 kilograms. We calculated the velocity at 4.46. And we want to add in then the force of friction. And notice that the force of friction is going to be a negative value because it is acting to slow that object down. And the force of friction can be found by taking the mass, which is 28,000 kilograms, and multiplying it times gravity of 9.8. So those two together would give me the normal force, and then the coefficient in the problem is given as 0.65. So all of those three things together would give me the force of friction. Okay, then the distances are unknown, and those two will end up giving me 0 as an answer at the end. Multiplying all of those out, we end up with a distance value of 1.6 meters that they traveled before coming to a stop. Welcome back, everyone, with your Sioux Falls physics teachers. Looking today at a glancing collision, and basically that's any type of collision where we deal with angles. So in this situation, we have two football players. One is running directly down the sideline. That one is over here with a velocity of 10 meters per second. The other one's coming in at an angle with a velocity of 12 meters per second. And again, notice that because they're tackled, they'll be moving together out of bounds. It is a perfectly inelastic collision. And that means that as we're figuring out the conservation of momentum part, we can treat them as a single object after they have collided. So let's get started here. And again, anytime you're dealing with angles, it's a good idea to go ahead and draw in the vector part of this. Notice that for the guy going down the sideline, it's probably not a real big deal because he is going along the vertical axes. Okay, so here's our y-axis. However, for the one that's coming in at an angle, we do need to have components for that. So we already have our resultant there at 12 meters per second. And we might want to kind of draw this out to the side to give ourselves a little bit more room. We will have a horizontal component to that velocity and momentum. And we'll have a vertical component and the angle that is given is 40 degrees. So to start with, we can do a little trig with this. Notice that the horizontal part would be the opposite side. So for opposite side, we'd be using sine. So the sine of 40 degrees is going to be equal to our horizontal velocity divided by the resultant, which is 12. And that gives us then a horizontal value of 7.7 meters per second. Okay, so this part up here is 7.7 meters per second. We can repeat the calculation, this time using the cosine for the adjacent side. And that adjacent side to the 40-degree angle is the vertical component. So using our adjacent over hypotenuse, again hypotenuse is 12 for the resultant velocity, we get a vertical component then of 9.2 meters per second. So now we have the two values for the components of the velocity, and now we're ready to actually calculate the conservation of momentum part. Now again, remember, it's a good idea when you're writing out the conservation of momentum for a glancing collision to do so specifically writing x and y directions. So in the x direction, we would have momentum 1 plus momentum 2 equals final momentum. And again, that's mass 1 times velocity 1 plus mass 2 times velocity 2. Afterwards, again, since they are moving together, when we do a perfectly inelastic collision, we combine the two masses and then multiply them times a single velocity because they are traveling as one object. Now, we do want to make sure that we note, so that we can keep this consistent, we'll make this guy over here object 1 and this guy over here object 2. So in the x direction then, and again remember, the reason we want to write that x out to begin with is so that remember everything in this equation needs to be in the x direction. Object 1, he has a mass of 90 kilograms. In the x direction, he has a velocity of 7.7. Okay, so that was the velocity that we just calculated out, 7.7 meters per second. In the x direction, object number 2 has 0 momentum. Okay, so he's not traveling at all in the x direction, he's just traveling vertically. And then if we put their two masses together, we have a total of 170 kilograms after they collide, and that then is multiplied times our final unknown velocity. So working out the algebra, we have an unknown velocity or a final velocity at the end of 4.1 meters per second. Now we're ready to go back and repeat that calculation, this time in the y direction. And again, we would, in the y direction, add the initial momentum of objects 1 and 2, and that will give us our final momentum. So m1v1 plus m2v2 is equal to our total mass, m1 plus m2 times final velocity. And notice at this time then, we just want to make sure we're working in the vertical direction only. So for object number 1, the 90 kilogram guy, the vertical part of his velocity was 9.2. And then notice that object 2, the guy traveling at 10 meters per second, is traveling strictly in the vertical direction. And so his 80 kilograms can just be multiplied times 10 meters per second, because his entire velocity was in the vertical direction. Again, their total mass together is 170, and that's multiplied times their final velocity. And doing the algebra and solving for the unknown, we get a final velocity in the vertical direction of 9.6 meters per second. Now, the final part of this question, of course, it says calculate their velocity. Well, velocity indicates we need a resultant. And so what we have currently is an x component and a y component. We need to draw those out. And again, notice that 4.1 is our x component of the final velocity, and 9.6 is the y component. And so our actual resultant then would be at an angle. If we go back to our original problem, we see that they would collide right here. Our initial player was coming in the vertical direction. The tackler was coming in like this. It does certainly seem reasonable that they would be traveling in that general direction when they're done. So let's take a look then at what the math would be to find that resultant velocity. We'll be going back to just the Pythagorean theorem. Okay, so we have our x component, which is 4.1. That's meters per second. Our y component, which is 9.6. And calculating the resultant velocity from that, we get a final answer of 10.4 meters per second. Now notice we are actually not completely finished yet, because a true velocity would include an angle. And so we also need to figure out what that angle is there, and we can do that by using the tangent. So opposite over adjacent, in this case the opposite is 4.1, the adjacent is 9.6. And solving that out, we get an angle of 23 degrees. Now notice that it would of course been perfectly acceptable to do this angle up here as well. The key is just to make sure that you have marked somewhere where that angle is written from, and in this case that would be 23 degrees from the vertical as the angle of their final velocity.
Alright, the Sioux Falls Physics gang is with you again. We're going to be doing another glancing collisions problem, this time involving two balls that have the same mass, but the mass is not given to us, so we'll talk about how that's going to come into play. But we have a red ball that's traveling at 0.75 meters per second. It's going to hit a white ball, again with the same mass, and that white ball is going to go off at a speed of 0.25 meters per second at an angle of 37 degrees. All right. We are going to assume that this collision is inelastic, and we're curious about the angle that the red ball is deflected at and that red ball's speed once the collision occurs. Okay, so got a little diagram already set up here for you that will show you how the red ball is going to come in and then how it would collide with the white ball. And so this is going to be using some of the concepts with momentum. So we know the red ball is traveling at a velocity of 0.75 meters per second. And so if I take about the velocity times the mass of the red ball, which we don't know, but that's okay, because really our masses are going to end up kind of canceling out here because all the masses are the same. But that would be the momentum of that red ball in the horizontal direction as it comes into the collision. Okay? Now remember, momentum must be conserved in all directions. So currently I have no momentum in the vertical direction before this collision happens. The red ball is only moving horizontally. All right? Now, we know that the white ball goes off at an angle of 37 degrees and has a velocity of 0.25. So its momentum as it goes off is 0.25 times m at 37 degrees. All right. Now we can do some trigonometry here and determine for the white ball both the horizontal and vertical components of that momentum. So just using our 37 degrees, we can easily figure out what the horizontal and vertical components are of that momentum. So using the sine of 37, we get a vertical component that is equal to 0.15. So really what I'm doing there is just taking sine 37 degrees is equal to the vertical component in the y direction. So we'll say the white ball's y direction momentum over the 0.25 m, okay? And that's how I'm getting my 0.15 m. And then I'm going to do the same thing now to figure out the horizontal is just take cosine of 35, okay? And when I solve for that, I get a horizontal momentum there of 0.20 times m, okay? So that's for the white ball. And now that I know those components of momentum for the white ball, that'll help me figure out the components of momentum for the red ball, okay? First thing, and this is the easiest part of this, is that we said initially there was no vertical component of momentum or movement. So if the white ball had a component of 0.15 in the downward direction, then the red ball must have a component of 0.15 times m in the vertical direction for its momentum. All right? The second thing that we must consider is that, remember that we had 0.75 times m of horizontal momentum from the red ball initially. We've used 0.20 m of that already for the white ball. That means that there has to be 0.55 times m momentum left over for the red ball in the horizontal direction. Okay? So if I kind of redraw the red ball's vectors here for momentum, all right, I've got 0.15 times m momentum in the vertical direction and 0.55 times m momentum in the horizontal direction. Now again, I can do a little trigonometry to get my resultant momentum, and that ends up being 0.57 times that mass. Again, the mass is the same for both balls and really is going to not be a factor here because we're dealing with the same mass for both objects. But 0.57 m would be my resultant, and then I can use some trigonometry to find this angle here, which would be about 15.3 degrees, okay? Now, keep in mind, this thing was asking initially, okay, at what angle will the red ball be deflected? Okay, well, we just found that at 15.3 degrees, okay? Now, the last question is, what will be the speed of the red ball? All right, and this gets a little bit more tricky here as we calculate this. Since we know that the momentum of the red ball, the resultant momentum is 0.57, okay, and we know that momentum is equal to mass times velocity, we could say 0.57 m equals mass times velocity. Now I have mass on both sides of my equation, so that can cancel out. And so really my velocity ends up being 0.57 meters per second for that red ball.